This is Kedar Rao in lab M03. This is the black hole mass video lab report. The main objective of this lab was to analyze a star revolving around a black hole and estimate the mass of the black hole by using the motion of the star. The result was that the mass was found to be about 2.2 times 10 to the power of 31 kilograms. Using this Python code that was given to us last week and the motion of the star, which was given to us in the WebAssign Excel spreadsheet, we can track the motion of the sun, which we can use to find the mass of the black hole. The initial conditions given to us are the mass of the star, which is 1.989 times 10 to the power of 30 kilograms, and delta t, which is 86,400 seconds, which is the amount of seconds in a day, and the initial position of the black hole, which is, in my case, -1 times 10 to the power of 10, comma 4 times 10 to the power of 10, comma 0 meters. So the momentum principle can be seen here in this section, where we use the initial momentum and the final momentum to find the derivative, basically delta p over delta t. And using this, we can find the two components of the dp dt, the perpendicular component, as we can see right here, and the parallel component right here. So now let's take a look at the actual model. So this is the data from my Excel spreadsheet, and right here you can see the force of gravity is the largest because the radius is the smallest, and right here, wherever it is above here, the force of gravity is extremely small because the radius is so large. So to find the radius, we used the black hole position, which was given to us in WebAssign, subtracted that from the star position, which was also given to us in WebAssign. It was the CSV file. So we did star.pos minus blackhole.pos, and that gave us our radius. To find the mass of the black hole, we used the radius we found, r, and the initial values of the mass of the star and the magnitude of the net force they found, which is equal to the delta p over delta t. And so we did the magnitude of F net times the magnitude of r squared divided by the gravitational constant 6.67 times 10 to the power of -11 multiplied by the star mass multiplied by the magnitude of the normal vector, which is basically just 0, 1, 0. So using this formula and the run we just saw, we can find the mass to be of the black hole to be 2.189 times 10 to the power of 31 kilograms, and the total observation time is nearly 4 Earth years. So now on to the what does it mean. So to answer this, I'm going to show you the motion one more time. So unfortunately, all my data, the only motion of my data is up to here, it doesn't go all the way around. However, FNet parallel will be, as the motion goes like this, the FNet parallel will be parallel to the motion always. FNet perpendicular will always be perpendicular, the 90-degree angle to the star's motion. So it will always be pointing towards the center of the orbit, which is basically to the black hole. So basically, the FNet parallel perpendicular and FNet just in general is exactly has the same value as delta p over delta t, and for FNet, and for FNet parallel delta p over delta t parallel, and for FNet perpendicular delta p over delta t perpendicular. So although these values are the same, the meaning behind these values are different for both. For FNet, for the FNet, FNet perpendicular, and FNet parallel, these values describe the force acting on the object, so the gravitational force acting on the object. And for delta p over delta t parallel, and delta p over delta t perpendicular, this basically shows the change in momentum over the change in time. So it does not actually describe the force acting on the object, it just describes the change in motion over change in time. That is essential to knowing the difference between Fnet and delta P over delta T. Another thing to keep in mind for the what does it mean question is that the force is what actually causes the object to move. So Fnet is what makes, or a force is what makes delta P over delta T have a value. So for the what if question, the answer is actually no, because since the mass of the black hole is different, the gravitational force that that affects the star is different. So that means the acceleration is different, which means that the momentum is actually different.